Hello again, everyone. Here we'll be discussing derivatives and integrals of vector functions that we described in the last section. Now let us recall from the last section as well that the limit of a vector function, so if the vector function is defined by these three, so it's a three-dimensional vector function where each component is a function of t, then its limit is just the vector whose components are each associated with that particular limit. So in other words, the limit of a function or of the vector function is the vector function whose components are the limit of each of those. So just pass the limit through each component basically. Because of this, the following theorem holds. I'm not going to prove it, but in fact I'll let you kind of look into it on your own. But it's actually fairly straightforward given the definition of derivative that we saw way back in Calculus 1. So, and what I'm talking about just to kind of show you is r prime of t in this case would be the limit as h goes to 0 of r of h plus t, or I guess we call it t plus h, but same thing, minus r of t all over h. The only real difference here is that since we're dealing with vector functions and vectors in general, then the dividing by h is multiplying by the scalar 1 over h, where you can bring things in and subtract these vectors just kind of like you would normally. So basically, because the definition of derivatives and the way we define vector subtraction and scalar multiplication, this holds. Which basically just says the derivative of a vector function is just the vector whose each component is taken derivative of. So very similar to limits, how we pass the limit through each component, now we pass the derivative through each component. So yeah, so I don't really know how to say it, but yeah, basically what we're doing is taking derivative of each component. And this is the same equation here, but just in ijk form. And here I say something in particular. So here I kind of emphasize on language a bit. So r of t here, or r prime of t I should say, is called the tangent vector of the curve defined by r of t. And the unit tangent vector is just the tangent vector, well, it's the unit vector that's in the same direction as a tangent vector. When we know how to find unit vectors, we just take the vector we want to find the unit vector of and divide by its magnitude. So we call this t of t, capital T standing for unit, well, the t stands for tangent, but capital T stands for unit tangent, I guess, in this case. Not to be confused with this lowercase t, which is our parameter. So I hope that's not too confusing. Now I haven't actually explained what this represents, but in three-dimensional space, if you imagine you have some space curve like this, for instance, call it r of t, then at any given point t, you'll have actually a tangent line, which is kind of interesting because it's in three-dimensional space. So kind of like we're used to in a two-dimensional space, only if you imagine the curve just bending somewhere in 3 dimensions. So this right here is r prime of t. So that's, again, that is the tangent vector. In actuality, this line is really just a vector like this, you can say, and this function, r prime of t, corresponds to every point that is on that line. Well, kind of on that line. It's every vector that's facing in this direction, or whichever direction we're going in, really. But again, this vector corresponds to whatever the point is. So it's a little hard to say without an example. So with that being said, let's just jump into this example then. So here we want to find the derivative of r of t being this. And then after that, we'll find the unit tangent vector that corresponds to this when t is equal to 0. So let's take a look. So the first thing to note is we want to find the derivative, which is r prime of t. And all we really have to do is take derivative of each component. So from an algebraic standpoint, or I guess calculus standpoint, there's no visualization needed. But relating to the visualization, I think, is where I'm kind of having trouble explaining. But let's just carry on. So derivative of the first will, of course, be 3t squared. Derivative of the second component requires product rule, and that's derivative of the first, which is 1, times regular of the second e to the negative 2, plus regular of the first, which is t, times derivative of the second, which is negative e to the negative t, actually, by chain rule, so that sign here changes to a negative. Derivative of sine is cosine. Derivative of sine of 2t is 2 times cosine of 2t by chain rule. Perfect. So this is the vector function, well, the tangent vector function. So if you plug in any value of t, you'll get the associated vector with that point when you plug in that t value into r of t, that'll give you the point on the space curve. So that I think describes it a little more specifically. Now, if we were to plug in t to be 0, when t is equal to 0, let's say, we get r of 0 gives us this vector, which is 0 for the first component. And that's going to be e to the negative 0, which is 1, minus 0, so it's 1 for the second component. Cosine of 0 is 1, so this is 2 times that, so it's this. Now notice that this vector here is not a unit vector, so to find the unit tangent vector, this is just the tangent vector when t is 0. And this is a tangent vector for any value of t. But to find the unit tangent vector, all we need to do is divide by the magnitude. Now the magnitude of a vector whose components are 0, 1, and 2 is just the square root of 0 squared plus 1 squared plus 2 squared. And we went over this when we discussed vectors. Now notice this is just 5, or square root of 5 really, so we need to divide by this. And there are a few ways of writing this, but I'm going to write it as follows. T of 0 equals 1 over the square root of 5 times the vector whose components are 0, 1, and 2. I wrote it kind of small there just for space, but I think we can make it out. Let's take a look. Yeah, I'll have to kind of squeeze in there. Let me move the camera a bit so we can see that. There we go. So I wrote this as 1 over radical 5 times the vector whose components are 0, 1, and 2. And like I said, there's a few different ways of writing this, because 1 over radical 5, if you want to rationalize, you can write it as radical 5 over 5. And then if you want to go even further, you can actually scale that into each component. But I just left it like this. And now we'll move on to discussing some properties of derivatives of vector functions. Right, so here are the properties I was discussing earlier. Suppose that u and v are any differentiable functions, vector functions. Differentiable just meaning that their derivatives exist on certain given intervals. C is a scalar and f is a real valued function. Then the following 6 properties hold, which are pretty nice. Now, the first 2 are pretty believable and pretty not too difficult to prove, just based on definition of things. Basically, this says derivative of a sum is sum of the derivatives over vector functions, which we kind of believe because that's certainly true for regular functions. The next says that scalar multiplication of a constant passes through. Now, this makes a lot of sense. Again, this is something that we kind of know from just regular derivative properties. But now the next 3 are quite remarkable. And they're actually all the same, but just with different products. So basically, these 3 here are actually different versions of product rule. That's all this really is product rule. We have product rule for scalar multiplication, we have product rule for dot product, and product rule for cross product. And it's exactly the same. You have 2 functions being multiplied together. Here you have a scalar multiplied by a vector, but they're both taken of the same variable. Here you have dot product of 2 vectors, and here you have cross product of 2 vectors. And the following holds with those corresponding products. Derivative of the first, regular of the second, plus regular of the first times derivative of the second. And that, I think, is pretty awesome that holds. I'm not going to go through proving these, but you can actually prove them in a very similar way that a product rule is proven. But for these last 2, you need to obviously leverage the definitions of dot product and cross product. It's a little involved, but quite doable. 6 here is literally just chain rule. So you have to have a vector function of a real valued function. You can't have a vector function of a vector function, because then each component would be 3 components, and it gets a little wild to imagine. So this really is just chain rule if you think about it. Okay. And that's really all I wanted to say as far as these properties go. And you know what, I wasn't going to do any examples, but we'll actually do an example that I think will use one of these 6. It's not a very obvious example though, so it's not calculative, it's kind of more conceptual. And then from there we'll move on to integrals finally. Right, so as previously mentioned, this example is more, I guess, conceptual opposed to calculative. But let's take a look. So we're asked to show that if we have a vector function whose magnitude is a constant, then it must be the case that the tangent vector function's derivative is orthogonal to itself for all values of t. Now let's remind ourselves, what does orthogonal mean? Well, orthogonal implies that the dot product of these 2 vectors is 0. So we want to show, so let's write WTS off to the side here, we want to show that r prime dotted with r results in 0. Now what this reminds me of is a product, obviously. So we have derivative dotted with that. So I think maybe if we get something as far as the derivative of r times r, maybe that'll make sense. And let me kind of show with some scratch work over here what I mean by that. So if we had r times r, it's going to be dot in this case. So r dot r, we want to find the derivative of this, so let's use prime for that notation. This will be r prime r plus r times r prime. And these multiplications are really dot products. So if we can show that this is 0, then we can show that each of these are 0. And in fact, notice that they end up being the same because r prime r and r prime is actually the same. So what we get from this really is 2 times the quantity r dot r prime. And if we want to show that's 0, actually that's doable because notice here, what does this remind me of? Vector dot product with itself is its magnitude squared. So look at this. So here's what we have. So let's recall this property here. The magnitude of a vector, in this case a vector function, squared is equal to the dot product of it with itself. Oh, look at that. So we're getting somewhere. So now if we take the dot product, or not dot product, but if we take the derivative of this, then we actually get this coming out. Now, I didn't really write that in a nice way, but I think this is okay, even though it kind of wrote like shorthand. It actually still works. So normally I'd write r of t, and this prime notation really should be d over dt, but you know what I mean. We're taking the derivative of the dot product of r with itself, and we end up getting this by the product rule for dot products, which amounts to that, and we want to show that this is equal to 0. Now, so this part isn't quite sure yet. But what do we know about this? This is, well, it's this on one hand. On the other hand, it is the magnitude squared, derivative of that. And if the magnitude is a constant, call it c, what is the derivative of any constant? It's 0. So this must be true. Awesome. So I kind of showed it in kind of a weird way just because of my space here and also the shorthand language I'm using. But I guess you could say this, going this way. Maybe that looks a little better. The derivative of any constant is 0. If the constant is the magnitude squared, then the derivative of that is obviously 0 as well. And magnitude squared from this property here is just the function dot product with itself. And then derivative of that by product rule with dot products gives us this, which is this. So this implies that 2 times r of t times the derivative must be 0, and then dividing by 2 gives us exactly what our want to show is. So dividing by 2 gives us that equality indeed. Awesome. So now moving finally on to integrals. Now, the reason why this is true, what I've written here with integrals, is mainly again because of how limits are defined with vector functions. Since integrals are defined as sums, limits of sums, from Riemann sums, if you remember that from Calculus 2, this actually comes about basically due to, again, that definition of limits from vector functions, but also from summation properties of vectors. So the sum of a vector is the vector of it, or is the sum of its components. So sum of the components of each of those vectors. So from those basically definition of limit and definition of vector summation, we end up getting this coming out. And this is true for definite integrals. And from this, we can actually define an indefinite integral for vectors in a very similar way. In fact, if you remove the limits, that is true, but that's more of a definition than an actual theorem that's true from other things. But remember, what that indefinite integral means is just antiderivative. So we use that symbol for antiderivatives. And from this, well, we actually get a theorem out, which is equivalent to the fundamental theorem of calculus, but now only with vector functions. And it basically says what you'd expect it to say. The integral from a to b of r of t is equal to the antiderivative of r of t evaluated between b and a, meaning you plug in the top one minus plugging in the bottom one, where capital R prime is lowercase r. So in other words, capital R is an antiderivative, any antiderivative of lowercase r. And now for this example, we don't have too much space, but let's see if we can squeeze it in. I don't think we'll be able to. But you know what, just so I'm not squeezing it in, because actually we kind of could, I'm going to erase, lift it up, and then we'll continue. Okay, so I've erased things, lifted it up, and let's see if we can continue. Let's see. Well, we want to find the antiderivative of this. And again, just to recall our notation for indefinite integrals, the antiderivative of r of t, or integral of r of t dt that is just the antiderivative of each of these components. Antiderivative of cosine is positive sine. The 2 stays because it's constant. Antiderivative of sine is negative cosine. Antiderivative of 2t is 2t to the 2 over 2, which is t squared. That certainly makes sense because derivative of t squared is 2t, so that's good. But now considering the limits, so again, this is true because the way we define indefinite integrals for vector functions. But considering the limits now, we need to evaluate this guy between the limits. Meaning, we need to plug in the top one minus plugging in the bottom one. So let's see if we can do that. When we plug in the top one, we get 2 times sine of pi over 2, negative cosine of pi over 2, pi over 2 quantity squared, and then minus the vector you get when you evaluate this as 0, which notice sine of 0 is 0, cosine of 0 is 1, so it's negative 1 for the second component. 0 squared is 0. Good. Now, let's see, what is sine of pi over 2? Sine of pi over 2 actually is 1, so this is 2. So let me write that here. Cosine of pi over 2, on the other hand, is actually 0, so that's negative 0, which is just 0, of course. Pi over 2 quantity squared is actually pi squared over 2 squared, which is 4. And then minus this, and you know what, I'll bring in this negative as a scalar to make this addition, and just negate each of those components. We get positive 1 for the middle term. And then if you add 1 to this, or if you add all of these, actually, you're just adding 1 to the middle term, really. And that's 2 comma 1 comma pi squared over 4. Fantastic. And maybe it would have been a little bit of a stretch to squeeze it in the space we had. But there we go. So we saw an example of integrals. We saw a bunch of properties of derivatives. And mainly we spoke of derivatives, not integrals. But everything we know of integrals are true because of what they correspond to derivatives. So we spend more time with derivatives opposed to integrals. But if you try some of the homework problems, you'll kind of get a handle, hopefully, on each of them. So I hope you enjoyed this video. And in the next video, there's more to come. So see you in the videos for that. Hope you enjoyed this. Thanks for watching, and I'll see you then.